This video discusses series circuits. So a series circuit is defined as a circuit where all the current through one series device also flows through the next series device. So if we look at this circuit here on the left, we can see that any current that's going to flow out of the top of the voltage supply here, so any current that's going to flow out of here is going to come through resistor 1, and it's going to continue on, and it's going to go through resistor 2, on in and through resistor 3, all the way back to the voltage supply. So remember, for a current to flow, it has to have a complete path. And so the current is the same everywhere within this circuit. So all the current flowing into resistor R1 is coming out of resistor R1 and going into R2, coming out of R2 into R3, and coming out of R3 and going into the power supply. So these resistors are in series. Now, if we look at this circuit over here, we have the current's going to flow through, out of E, through resistor R1. So R1 is in series with E. So R1 is in series with E. But when it comes over here, there's two resistors. Right here at this point, the current now can make a change. It can split. Part of it can continue on to the right and go through this far right resistor, and part of it can split here. So this here becomes a parallel branch where some of the current can go through one side and some of the current through the other. And so this is not in series. Now when we come down through these two resistors and we come over here, at this point here they join back up and we have the same current. So this same current now is going to flow through R3 and up through and into the battery. So R3 is in series with the battery, and R1 is in series with the battery. So these three devices are in series, but these other two are not in series. Alright, so if we have a series circuit, so this one is not series, so I'm going to remove that one. But this is a series circuit, and so whatever current is going to flow through R1 is also going to flow through R2, back through R3, and then into our power supply. So the total resistance then of this circuit is defined as being the sum of the three resistors. So R1 plus R2 plus R3 gives us R total. So R sub T here is the total resistance for a series circuit. So again, this is for a series circuit here. Alright, so for the series circuit, the total resistance is equal to the sum of those resistors. Now, if R1 was the exact same value as R2, and the exact same value of R3, then the total resistance, you could just say it's 3 times whatever the value of those three resistors are. So if the resistance is equal, so this down here is basically saying equal series resistors. Then it's N, which is the number of resistors, times the value of resistance. So if we know the total resistance and we know the supply voltage, then Ohm's law, remember this here in this box is actually Ohm's law. So Ohm's law tells us this is Ohm's law. Ohm's law tells us that the total resistance is equal to the voltage divided by the current. So if we knew the current and we knew the voltage, we could calculate the total resistance. Or if we've already calculated the total resistance from this equation up here, then we can, and we know the voltage, then we can calculate what the current is through that series circuit. Here's a simple two resistor series circuit. So we have R1, which is 220 ohms, which is in series with R2, which is 100 ohms. So the total resistance, of course, then is the 220 ohms plus the 100 ohms, right? Which means that it's 320 ohms. Now remember, if we're going to put this in Blackboard, we have to put 320 period, and then we can either draw the omega symbol or we could simply type in lowercase ohms. Okay, either one of those would be correct. But remember that because there's a 0 there and we need 3 digits, we need to make sure that we put that decimal point there. That decimal point is telling us that all 3 digits, including the trailing 0, are important to us. Alright, so given that the total resistance is 320 ohms and we know the voltage now, according to Ohm's law, we can calculate the current. The series current is equal to the 8 volts divided by the 320 ohms. And so we can pop over to our calculator here. I'm going to use the octave program. So we're going to have the current I is equal to 320 volt, or 8 volts divided by 320 ohms, which gives us 0.025 amps. So again, if we're going to put this into Blackboard, then this current, the answer would be 25.0 milliamperes. So remember, A stands for amperes. So 25.0, and then don't forget there should be a space there, and then milliamperes, and that would be your answer and to enter into Blackboard. Alright, so if we look at that, we can now still, we can come over to R1 and we can apply Ohm's law and we can find out what the voltage drop is across R1. So we can find the voltage V1, which is the voltage dropped. If we put a voltmeter on this resistor, we can measure this voltage, V1. So V1 now becomes the 25.0 milliamps times the 220 ohms. Again, we'll flip over to our calculator. Alright, so I already have I stored in octave here as a variable, so I can just take V1 then. So V1 is equal to I times the 220 ohms, and we find that that is 5.5 volts. Okay. So V1 then is equal to 5.5 5.5 volts. Okay. So again, if I'm going to put that in a blackboard, it would have to be 5.50 because we need 3 digits and then a capital V, a space and a capital V for voltage. So that would be our answer if the blackboard was asking what is the voltage drop across V1, 5.5 volts. Alright, and so likewise we could say, well, what is the voltage V2? What is the voltage drop across R2? So that V2, again, Ohm's law is the current times the resistance, which the current was 25 milliamps, and the resistance now is 100 ohms. And so the current, or the voltage across V2 then, 100 times 25 milliamps gives us 2.50. Remember, we need that extra 0 volts. So 2.50 volts. So now if you look at this, if you look, right, our supply voltage E is 8 volts. Our supply voltage E is 8 volts. And our voltage drops V1 and V2. So the voltage drops V1 and V2 is 5.50 plus 2.50, which is equal to 8.00 volts. So what we see here then is the supply voltage is equal to the sum of the voltage drops within the series circuit. Right? This is actually kind of known as Kirchhoff's voltage law. We'll look at that here a little bit later. Alright, so here we have a circuit with 3 resistors in series. So again, all the current that's coming into R1 comes out of R1 and has to flow into R2. All the current flowing into R2 is coming out of R2 and flowing into R3. So this current is the same through this entire branch, because whatever's coming out of R1, it has no choice but to go directly into R2. And whatever is coming out of R2 has no choice but to go to R3. There's no other way it can go. So these again are in series. And so the total resistance is the sum of these 3. So our total then is 100 plus 220 plus 330. So that gives us 650 period ohms. Right? And so that is that total resistance. Now, if we look at this circuit down here, it's really the exact same circuit, but the only difference is that R2 is in a different location. However, all the current that's going to flow through R1 is going to then, it must go through R3. It has no other choice but to go through R3. When it comes out of R3, it's got no other choice than to go through R2. So it doesn't matter what the order of the resistors are. Okay, this is still 650 ohms. So it doesn't matter, you know, we only have 3 resistors, so there's only like 3 different ways you can you know, a few different ways you can do them. But so now if we try to calculate the current, we first have to find our total. Well, we already found our total was 650 ohms. So now, using Ohm's law, we can calculate the current. So the current over here, I, is equal to E, the total current, the total series current is the supply voltage divided by the total resistance. And that current then is going to be 8 volts divided by 650 ohms. And so that becomes, flip back over to my calculator, so now I have I equals still 8 volts, but now we're dividing it by 650. And so our voltage, or our current now, is 12.3 milliamps. So again, the current is 12.308. So let's write that all down. So it's 12.308 milliamperes. Okay. So if I was going to put it in Blackboard, I would just record the 12.3 milliamperes. So I would not worry about the 0.8 to go into Blackboard. I would just put the 3 significant digits. However, when we calculate the voltage of the voltage drop of each one of these, so remember, if we want to measure the voltage drop across a single resistor, we measure that in parallel. And so we measure that, or we can calculate it using Ohm's law, so that V1 is my current, which is simply I. So it's I, or I series if you want, times R1. And then we have V2 would be that same current because it's in series. So I series times R2. And V3 is I series times R3. Okay. So I'm going to flip over to the calculator here and calculate those. So we're going to have V1 is equal to I didn't put an S here, so it was just I times the 100 ohms. And so that is 1.2308 volts. V2 is equal to I times 220, which is 2.707 volts. And V3 is equal to I times 330 ohms. So that's 4.0615. All right. So if we're going to put these in Blackboard, okay, let me copy these and put them over here. All right. So if we're going to put these values in Blackboard, we would record V1 to be get back to my pen. So V1 is going to be 1.23 volts. And V2 is going to be 2.71 volts. And V3 is going to be 4.06 volts. 4.06 volts. All right, so if we tried to add those up, all right, so if we added up .23 plus 2.71 plus 4.06, okay, you can see that we get 8 volts. Now, you have to be careful though, because sometimes when you round up and you just cut it down to 3 digits, it may not come up to be exactly 8 volts. Okay? So it might be a little bit off. So actually, if I change my format to what's called long format here, let's see if it still reports it to be 8 volts. So it is, let's see, we've got a 6 and a 3 and a 1. Yeah, that's a 4. So it did add up to be exactly 8 volts. All right, so we got lucky in that case. But in general, when you record your values, you want to, again, keep your digits out to 5 decimal places, so that if you need to do the calculations with these values, you keep all of those, so you don't try to round up until you are putting the answer into Blackboard. So you only round when you're putting the answer into Blackboard. But as we see, when you take these 3 voltages, V1, V2, and V3, and you add those all up, so when you add up all the voltage drops across all these resistors, they're equal to the supply voltage. So the voltage drops across all the series resistors is equal to the supply voltage. Or we could look at it another way. I'm going to go up here. I'm going to start here at ground at 0, and I'm going to go up. So when I went up, notice this is a positive. So I went up 8 volts, right? That was my supply. I went up 8 volts. Now I come through here. Now notice, as I went up, I looked at the sign as I came out. Okay, so I looked at the sign as I came out, and I said that's a positive. So I go up, and that's a positive 8 volts. And then here, then, if I look at the sign as I come out, this is a negative sign. So I'm going to subtract my 1.23 volts. And then when I come through this resistor, again, it's a drop. That's the negative, indicates that it's a drop. And so I'm going to subtract the 2.71 volts. And then I'm going to go through this resistor, and again, as I come out, I see the negative sign. And so therefore, I'm going to drop the 4.06 volts. All right, so if we write that, we have plus 8 volts minus V1, which is 1.23 volts, minus the 2.71 volts, minus the 4.06 volts, and that's all equal to 0. Right. Now, if I wanted to, I could go the other way. Let's say that we start here, and let's go backwards. Okay, so let's start here, but now I'm going to go counterclockwise. So if I go counterclockwise, and I come out here and I look, oh wait, there's a plus sign. So I went up 4.06 volts. So I went up 4.06 volts. And then as I come through here, I look at that, oh, that's a plus sign. I went up another 2.71 volts. And then as we go through here and I come out, it's a plus sign. So I went up another 1.23 volts. And then as I come through here, now I went down 8 volts. So now I've gone down 8 volts. So if we do that, that's going to give us, again, we're going counterclockwise, so we're going positive 4.06 volts, positive 2.71 volts, positive 1.23 volts, that's a V there, minus 8 volts is equal to 0. All right, so it doesn't matter whether you go clockwise or counterclockwise as long as you are consistent. All right, however, I just recommend for everybody to always go clockwise. All right, so when you do this, just always go clockwise. just be consistent. All right, so you don't have to go counterclockwise, or I mean clockwise. You can go counterclockwise, as I did in red just there, but just always go counter clockwise, and that's just good practice. All right. So, but anyhow, this really is basically showing Kirchhoff's voltage law. Kirchhoff's voltage law says that as you go around a loop, right? As you go around a series loop, and if you go around a loop, any loop inside of a circuit, the voltage rises are equal to the voltage drops. Or as you go all the way around, the voltages, the sum of the voltages in any loop, the sum of the voltage will end up to be a zero. Okay, that's Kirchhoff's voltage law. All right, so let's just take a quick look here at a couple of cases here where we have something going on in our circuit. So we had these three resistors, R1, R2, and R3, that were in series, but now I've got this short. So there's this short here. So you can see that this this wire somehow got right across here between this connection up here and this connection up here, down here. And so what happens is current is going to follow the path of least resistance. So the current I is going to flow through the path of least resistance. All right, so we know that all wire has resistance. Every device actually has some resistance. However, a copper wire's resistance, we calculated a little bit of that in a previous class. We see that the resistance of a piece of wire is usually just a fraction of an ohm, where this resistor is 330 ohms, plus there's some other wire going on over here. So what that means is that the current is going to say, you're too much work, R3, I'm not going through you. And so what it's going to do then is the current is simply going to run through R1, through this short, through R2, and then back in. So the total resistance then of this circuit would be 320, and again, if we're putting it in Blackboard, don't forget your decimal point, ohms. So 320 ohms. All right, because it will bypass this resistor of 330 ohms, because it's much easier for it to just take the shortcut. And because whatever this wire is here, this wire has fractional resistance compared to 330 ohms of resistance. Now on the other hand, in this circuit further down here, we see that there's a short right here. So here's this short, and so in this case then, it's like, okay, I could either take the shortcut, or I could go through the 100 ohm, then through a 300 ohm, then through a 220 ohm and get back. All right, and so in this case now, this is a true short circuit here, so that the resistance, the total resistance is zero, or at least something very close to zero. There might be something out here, but for the most part, the resistance is simply zero. So in Blackboard, again, that would be 0.00, that's the special case of 3 zeros, omega. Okay, or you could type in ohms there, but those are short circuits. Now here is an open circuit. So we have, all right, so we've got R1 is connected to R3, but right here at this point now there's a break in the wire. All right, that break in the wire is considered an open, and so the resistance is really, really big. Now we've all seen lightning, so we know that electricity can flow through the air. However, for that to happen, it has to just be a very big value. So what we say is that the resistance here is infinite. All right, so the resistance is infinite. So this is the infinity symbol here. So the resistance would be infinite ohms. And what that's saying is that's just a really, really, really big resistance. All right, so just kind of as a recap here, we have series circuits says that all the current flowing into that device, whether it's a resistor or a battery or any other device, all the current flowing into this one device and coming out of that one device and then going directly into another device, those two devices would be in series. And the total series resistance is simply the sum of those voltages. Right? And Ohm's law always applies, right? This is a physical law. Ohm's law is a physical law, so it always applies. You just have to apply it appropriately. So when we're talking about a series resistive network here, we first find our total, and then we can use the total supply voltage to find the total current into that series branch. Okay. But then down here we also found that we could, after we know the resistance and we already found the current, we could use Ohm's law again to find the voltage across just this one element. And we also saw that when you add up the voltage drops across resistors, you add up all your voltage drops across resistors and you add up your supply voltages, and add those all together and you end up with 0. And so that is what they call Kirchhoff's voltage law. And Kirchhoff's voltage law, again, is a physical law. It's a guarantee that if you go around a loop and you're adding up voltages around that loop, when you get back to the point that you started, so you start at this point and you go all the way back and you get back down to this point, then whatever voltages you went up, you came back down and you end up at 0. Okay, so all the voltages around any loop in any circuit, I don't care what the circuit looks like, you pick one loop and go through that loop. When you get done, you're back to 0 volts.